Hi, it's Mr. Jensen. Today I'd like to go over Earth Science Reference Tables page 14, the selected properties of Earth's atmosphere. So at first glance it may look like one big graph, but it's actually three that share one y-axis. That y-axis that they share is altitude, and as you go up on the page, you increase in altitude. The first graph is temperature zones. The second graph is atmospheric pressure. The third graph is water vapor. So I'm going to start with temperature zones. The very bottom of temperature zones is supposed to represent sea level on Earth. So if I draw a person here, this person is standing at sea level on the crust of Earth. We call this layer of the atmosphere the troposphere. It's the one that we are living in. So if you walk outside right now, you are going to be in the troposphere of Earth. All right, so how does the temperature change as you move up in it? So at ground level, at sea level, it would start at 15 degrees Celsius. As you go up in altitude, or an increase in altitude, it goes down to negative 55 degrees Celsius. So the troposphere, as you increase in altitude, the temperature decreases. So if we were in class, I'd have you put decreases in the troposphere area to remember that as you go up in altitude, increase in altitude, you have a decrease in temperature. So then you get to this dashed line, that's where the troposphere ends. You call it the tropopause. And so at the tropopause, what happens is your temperature trend changes, it switches, and it increases as you move up in the next layer called the stratosphere. It goes from negative 55 to 0. 0 degrees Celsius is cold, but negative 55 is colder. So the stratosphere, I'd have you guys write, increases. Then you get to the stratopause, which is the end or the top of the stratosphere, and the temperature trend changes again as you go up in the mesosphere, and it gets colder. So I would write decreases. I get to my final layer called the thermosphere after I cross over the mesopause, and in this layer, the temperature increases. So why does it flip-flop as I go up? Let's figure that out. So in the troposphere, the bottom of the troposphere is going to be the warmest because there are the most particles there. The particle density is the highest at the bottom of the troposphere. So I'll try to draw that in really quick. At the bottom, there's a lot of particles. As you go to the top, there's fewer. Particles are able to absorb heat, so if you have more particles, then you can have more heat, which causes a higher temperature. So generally, more particles is going to mean higher temperature. So now I go to the bistratosphere, and this is a mystery because I just said as you go up, there's less particles, and I told you if there's more particles, it's warmer. So the stratosphere isn't about the amount of particle density, it's about the particle that's there. The particle that's there is called O3. It creates the ozone layer. The ozone layer is a very important layer in the stratosphere. What the ozone layer does is it absorbs most of the UV radiation that comes from the sun. UV is ultraviolet. Ultraviolet radiation is responsible for something like a sunburn. Some of the ultraviolet gets down to the ground level of Earth, which gets down to sea level, and it could give you something like a sunburn. But most of it is absorbed by the ozone. The example that we usually give is that if there was no ozone and all the ultraviolet radiation was able to hit the ground and get to us, it would be so much radiation that humans couldn't even live here. As you go into the mesosphere, it's just the basic rule with the particles. There's less particles at the top of the mesosphere, so the temperature is going to decrease again. The thermosphere is a little funny because there's barely any particles there. So there's not much heat transfer. So the thermosphere, there's a really, really small amount of particles. But those particles are directly hit by sunlight. So the very small amount of particles in the thermosphere are directly hit by the sun. There's nothing that's absorbing any radiation from the sun that's protecting them from sunlight. So the very small amount of particles there are getting directly hit, and the very small amount of particles are very, very hot. Now, for example, if you were in the thermosphere, you would feel cold because there's barely any particles that are going to make contact with you. So you would feel cold in the thermosphere, but that's because there's a lack of particles. But we say the thermosphere is hot because the small amount of particles that are there are incredibly hot. All right, moving on to atmospheric pressure. At the bottom or at sea level, you have a pressure of 1. That means that there's 1 atmosphere on top of you. As you go up in altitude or increase in altitude, your pressure will go down, not all the way to 0, but to very low amounts of atmosphere on top of you. So as you go up in altitude or increase in altitude, the pressure will get lower. Now, water vapor is going to be an area where people make a small mistake, and that is that they think that the stratosphere has a lot of water vapor in it because the water vapor title is between the lines that dictate the altitude of the stratosphere. So what I would do if I would edit the Earth Science Reference Table is I would put the title with the other titles to be less confusing. So the idea here is that the water vapor on Earth is actually all in the troposphere. Just a little tiny bit gets into the stratosphere. But for the most part, we just say that most or all of the water vapor is stuck within the troposphere. So why does it get stuck within the troposphere? This is because water vapor comes from liquid water. Most of the liquid water on Earth, we'll say, is in the oceans. So if ocean water gets warm, it could turn into water vapor. Water vapor is a gas which has a low density. Water vapor can move up in the atmosphere if it has a low density. That water vapor moves up to the troposphere where it gets colder as you go up. If it gets cold, that water vapor, which is a gas, can turn back into a liquid. Those liquid water droplets will turn into clouds. When those clouds are filled with liquid water, that liquid water can fall back down to Earth as precipitation. So water vapor gets stuck in the troposphere. All right, so that's a general overview of page 14 of the reference tables, the selected properties of Earth's atmosphere. And if you have any questions, you can ask on Google Classroom. I hope you have a